this video, we will be discussing about find eventual safe states. There is a directed graph of n nodes with each node labeled from 0 to n minus 1. The graph is represented by a zero index 2D integer array graph where graph of I is an integer array of nodes adjacent to node I, meaning there is an edge from node I to each node in graph of I. A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. Return an array containing all the safe nodes of the graph. The answer should be sorted in ascending order. So what they are saying is that in the input, we are given this 2D integer array graph, right? Now here it is denoting the edges, right? So basically, this is the index 0, this is 1, this is 2, this is 3, 4, 5, and 6. So this is denoting that from node 0, we have a directed edge towards node 1 and node 2, right? So if we draw the graph, so first we have node 0, which is having a directed edge towards node 1 and node 2. Then node 1 is having an edge to node 2 and 3. So node 2 here and then node 3 over here. Then node 2 is having a directed edge towards 5. So this is node 5. And then from 3 we have a directed edge towards 0, right? Then from node 4 to node 5. So we can create a node 4 over here and a directed edge towards 5. And then from 5 we do not have an edge, outgoing edge, and from 6 also we do not have, but we will have the node 6 over here, right? Now they are saying, they are mentioning two things over here. One is a safe node and other one is a terminal node, right? So firstly, what is a terminal node? So if from any node there are no outgoing edges, so basically outgoing edges are the one which move away and incoming are the one which come to that particular node, right? So if a particular node does not have any outgoing edges, then it is considered as a terminal node, right? So if we see in this particular graph, node 6 is not having any outgoing edges, right? So we can say this is a terminal node. Node 5 also is not having any outgoing edges, so this is also a terminal node. Only these two are the terminal nodes, right? Now here we need to identify the safe nodes, right? Now what is a safe node? So if from a node there are multiple paths, right, and all of that path leads to either a terminal node or a safe node, right, then this node is also considered as a safe node, right? So basically, if I have a node and every possible path from that particular node leads to either a terminal node or a safe node, right, then this particular node is considered as a safe node, right? So if you see over here, this is a terminal node, right? We are not having any path from it, right? So this will be a safe node, right? So basically we can make the conclusion that all the terminal nodes are safe nodes, right? So we can just say that the path from the node should lead to a safe node. If all the paths are leading to a safe node, then this is also a safe node, right? If there is at least one path from this node which is not leading to a safe node, then this will also not be a safe node, right? So if we look at our graph, so we see over here, node 6, we can see there are no paths, right? So this is a safe node. So let's mark it as safe. Then from node 5 also, we are not having any path, right? So this is also a safe node. Then from node 4, there is only one outgoing path, which is this one, and that is eventually leading to a safe node. So this is also a safe node, right? Then if we look at node 2, only one path is there and that is leading to a safe node. So this is also a safe node. Then if we see for node 0, from node 0, we are having two paths. One is this and one is this. This one is leading to a safe node, but we need to check this one as well, right? So from here, it will go to 1. From 1, we can go to node 2, which is a safe node, but we also need to check this particular path, right? So this path is leading to node 3 and node 3 is leading back to node 0, right? So now did you observe one thing over here? From node 0, we went to 1, from 1, we went to 3, and from 3, we went to 0. So this is a cycle that was formed, right? So can we conclude from here that this path, this cyclic path will never be able to reach a safe node, right? Because this is an infinite cycle, right? None of these nodes are safe nodes. So this path will never be able to reach a safe node, right? So we can say that wherever a cycle exists in our graph, then whatever are the nodes which are part of this particular cycle, those nodes will never be safe nodes, right? All the other nodes which are not part of any cycle, they will be our safe nodes, right? So this is the conclusion that we have made, right? Now how we will identify such nodes? So we can see for each node, we want to know that each of its path should eventually lead to a safe node, right? So And if that path gives a safe node, so you will come back and you will traverse the next path. If that also gives you a safe node, you will come back and you will go to the next path and so on, right? So does this give you an idea of applying DFS over here? Depth first search, right? Because we can check the entire path starting from a particular node and check if it is leading to a safe node or not. If it is, then we can come back to this node and check another path. And if in any case we are not able to reach a safe node, that means it is a cycle, then we can say that this node is not a safe node, right? And also all the nodes which were present in that particular path which didn't lead to a safe node, all those nodes will also be unsafe nodes, right? So we will be applying DFS over here for each of the nodes, right? For each of the nodes we will apply DFS. And since we also want to know that when a cycle is being formed, right, from 0, when we went to 1 and then 3 and then again to 0, so there should be something which tells us that this 0 has been visited second time, right? So what we will do is that we will create a hash map, right? This hash map will store whether a particular node is safe or not, right? So basically this will be a key value pair where key will be the node and value will be a boolean, true denoting that it is a safe node and false denoting that it is a unsafe node, right? So as I said, we will be applying DFS for each node in the graph, right? So basically we will be running a for loop starting from 0 going till 6, right? So firstly, we will apply DFS for node 0, right? Now for node 0, what are its neighbor 1 and 2? So first you will go to this particular path, then you will come here, then you will come here. So somewhere you have to store that you have visited 0, you have visited 1, you have visited 3. Only then you will be able to identify that you are visiting 0 for the second time when you come to this path, right? So what we will do is that whenever we are applying DFS for any of the node, we will mark it in our hash map with the value as false, right? Initially, we are saying that I have started my DFS for this node. Basically, I have visited this node and right now I am assuming it is not a safe node, right? And as soon as I consider all of its path and all of its path are leading to a safe node, I will come here and update it to true, denoting that this is a safe node, right? So now we will be at node 0. From here, when we will apply DFS, we will go to node 1, right? So we will update 1 over here with the value as false. Then from 1, we will go to node 3, right? Now node 3, we will update here with the value as false, right? Now this node 3 is going to node 0. Now node 0, we can see it is already present in the hash map with the value as false. Now this is denoting that we are visiting 0 for the second time, and since its value is false, so this is a cycle that is being performed, right? So as soon as when we are visiting a node and it is already present in our hash map with a value as false, we can say this is a cycle and we can return from this node, right? So basically this node will return a false over here, 3 will also return a false and 1 will also return a false. So eventually 0 returned false for the first path itself. So we won't push this 0 in our answer because this is not a safe node, right? Then we will apply DFS for the next node, which will be node 1, right? So for node 1, we will check in the hash map, node 1 is already present with a value as false. So then that means we have visited node 1 already, right? And it is not a safe node, right? So we will not visit its paths again. We will move on to the next node. So next node will be node 2. Node 2 is not present over here, so we will perform DFS, right? So node 2, first of all, we will update 2 to false over here. Then its neighbors are node 5 only. So we will update 5 to false over here, right? Now for node 5, there is no neighbor, right? So then that means this is a safe node. So we will update this to true, right? So this 5 will return a true to node 2. Now node 2 is not having any other path. There is only one path which returned true. So we will update 2 also to true because this is also a safe node, right? So this node 2 will return a true now. Now in our for loop, since 2 returned a true, we will push 2 into our answer, right? Then the next node for DFS will be node 3, but node 3 is already present in the hash map with the value as false. So we will move to the next node. Next node is node 4. It is not present in the hash map. So first of all, we will mark it as false over here. And then for node 4, the neighbors are node 5. Node 5 is already there with the value as true, right? So this will return a true and eventually 4 will also be updated to true over here, right? And then this 4 will return a true, right? So since this returned a true, so 4 will also be pushed back into our array, right? Then the next node will be node 5. It is already present in the hash map with a value as true, right? So this will return a true and it will be pushed into our array, right? Then the next node will be node 6. It is not present in the hash map, so we will perform DFS. So first of all, in the hash map, 6 will be updated to false, right? Now 6 is not having any other neighbors, right? So this will be updated to true, and this node 6 will return a true, right? So since this returned a true, 6 will be pushed back into the array, and this is our answer, right? And if you see, all the nodes over here are sorted in increasing order. Why? Because we were performing the DFS starting from 0 till the last node, right? So that is the reason these are already sorted, and this is the answer. These are all the safe nodes, right? So this is what we need to do. Now let's quickly look at the code. So first of all, let's take the total number of nodes, which will be equals to graph dot size. Then let us create a map for marking the node as safe or unsafe. So we will create an unordered map. The key will be an integer and the value will be a boolean. Let's name it safe, right? Then we need an answer array for storing our answer, so we will name it result, right? Now what we need to do is that we need to apply DFS for each of the node in our graph. So we will run a for loop of I starting from 0 going till n and then I plus plus. Now inside this we will call our DFS function, right? And if that DFS function returns us a true, then that means that it is a safe node, so we will push it into our result, right? So if DFS of I, and what all things we need to pass, we will have to pass the graph and the safe map, right? So if this is returning us a true, then that means node I is a safe node, so we will push it into our result, right? And then at the end, from here we can return the result, right? Now let's try to create the DFS function. So this DFS function will return us a boolean. Its name will be DFS. It is receiving a node, then it is receiving a graph, which is the vector of vector. We will pass everything by reference, and then it will receive the unordered map, integer, comma, bool. The name is safe, right? We will also pass it by reference. Now, inside this, first of all, we need to check that whether this particular node is already present in the map or not. If it is already present, then that means we have already visited it, and we will return from here itself. We won't apply DFS, right? So we will check that if safe dot find node is not equals to safe dot end, then in that case we will return this value, right? So if this node is already present in our map, then whatever is the value, true or false, it will return it, right? Otherwise, if it is not present in the map, then that means we are visiting this node for the first time. And since we are visiting it for the first time, we will mark it as false inside our map, right? And then we will update it accordingly, right, as per the neighbor's value, right? So now we will check for all its neighbors. So for auto neighbor in graph of node, right, what we will do is we will apply DFS for the neighbor, right? So now if the neighbor returns as a true, that is okay. But if the neighbor returns a false, then that means this node cannot be a safe node, right? So here we will put a condition that if not of DFS of neighbor, comma graph, comma safe. So then that means some of the neighbor returned us a false. So our current node can also not be a safe node. So in that case, we can return from here itself. Now from here, either we can return false or we can return this also. Because as you can see here, we have updated the value to false only. So if we return this or we return false, both ways it is okay, right? Now if for any of the neighbor this condition was not true, then that means all of the neighbors returned a true. So this particular node will also be a safe node, right? So out of this loop, we will update its value to true, and then from here either we can return this or we can return true. Both the ways it will work, right? So this is what our code looks like. Let's try to run this now. So as you can see over here, first we are iterating for all the nodes and we are performing DFS, right? But in our DFS, each of the node is being visited exactly once, right? So the time complexity of this code will be V plus E, where basically V are the number of nodes or the vertices and E is the number of edges that you have in your graph, right? And for the space, we have used an extra space over here for storing all the nodes. Basically, whatever are the number of nodes n, that will be the size of this map. And since we are performing DFS, so the recursion stack will also take some size, right? So we can assume that the space complexity will be also order of V plus E, right? It is 2V because we have taken an unordered map over here, but since this is a constant, so we can assume this is our time complexity and space complexity, right? So let's submit this now. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.